Good morning, everyone. In today's lecture, we'll talk about counting processes. If you remember, last time we talked about exponential distribution. And today, when we talk about counting processes, we will have the two ingredients ready to discuss Poisson processes. Okay, so in many applications in engineering, as well as in real life, we count the arrivals of things, such as the arrivals of packets to a communication system, the arrival of emails to my server, the arrival of customers to a store, arrivals of photons to a detector, etc. In many physical and real-life phenomena, we count events that happen at discrete instants in time, one by one, sort of. So a model, a very strong and useful model that we use to characterize such arrival processes is the counting process. So a counting process is a stochastic process model or a random process model that we will define in three different ways, three different alternative ways. Let's write the first definition. A counting process is a stochastic process, n of t, that takes integer values such that n of t increases in time, does not decrease, that is, in time. Okay, so it's an integer valued process. It essentially counts the number of arrivals. Okay, so, and n of t increases essentially, it can increase by arbitrary integer values according to this definition, right? But we will see in many counting process examples that we have, that the probability of getting two arrivals at the same instant is going to be 0. In that case, the value of the counting process n of t will increase one by one. So let's draw a sample path. Suppose, without loss of generality, really, we start time at 0. And let's add something to this definition, in fact. Suppose n of 0 is 0. Okay? And at arbitrary times, we have arrivals to the process at which times the value of n of t increases by 1. So n of t, let me repeat, is the number of arrivals by time t. So if you will, let's have the values here 1, 2, 3, 4, etc. All right. Now, in this picture, it would be useful if I marked the times of the arrivals, the arrival instance, S1, S2, S3, etc. Right. Now, in addition to characterizing the stochastic process with the count of arrivals by time t, I could also characterize it by the sequence of the arrival instance, right? So let's do that. So if you will, basically, the counting process is equivalently characterized by the sequence Si, I greater or equal to 0, such that Si plus 1 is greater or equal to Si. And Well, let's just for completeness, let's set S0 to be 0. Okay? Set of arrival instance. Okay, that's one other way of characterizing the counting process. Now, I could also mark, let's take color. I could also mark, oh, that turned out to be black. The inter-arrival times. Suppose the time to the first arrival is x1, time to the second arrival is x2, time between the second and third arrivals is x3, and so on. Given that the process starts at 0, at time 0, I could equivalently characterize the process in terms of the inter-arrival times. So the counting process is equivalently characterized by the set of xi, okay, where the xi's are non-negative random variables. Non-negative random variables. So these are inter-arrival intervals. Therefore, they cannot be negative. But they can take any distribution. We will particularly focus on the case where the xi's are independent and identically distributed. And furthermore, we'll focus on the case where the xi's are exponential with some rate lambda, and that will give us the Poisson process. But for now, we're just addressing this counting process in the general case. So, how do you characterize the SI's in terms of the xi's? How about we call this Sn? Sn is given by the sum of xi's, right? Xi's. I from 1 up to n. Obviously. So clearly there's a one-to-one mapping between this description to that description to that description. They're all equivalent. The nice thing here is when you state it this way, when you define the counting process this way as a function of time, where t is the free variable here, it doesn't have to be time, obviously, but it's the free variable, and we define it as a continuous variable, right? It seems that this is a continuous time process, right? So it will take a lot to describe this. For every value of t, where t is real valued, we would need to specify an n. It appears at first sight. However, when you look at these equivalent characterizations, you see that it's really nothing but a sequence of values that characterizes the process. But that's much easier. This shows that really the counting process is a discrete stochastic process, right? Fewer dimensions in that regard, right? This is much easier, right? We can count these random variables that go into the description of the counting process. Okay, so this is the relationship between the nth arrival time and the inter-arrival durations. How about a relationship between the values that n of t takes and Sn, the inter-arrival instance? We can construct certain relations between them. let's try to tie n of t and Sn together in terms of events written in terms of each of these. So think about, first of all, Sn, the event that Sn is less than or equal to Sn is less than or equal to t. How can you write this in terms of n of t? So take some time t. This tells us, this event tells us that at time t, the number of arrivals so far is what? This tells us that Sn is at or before time t. So what can you say about the number of arrivals by time t? Yes, please. Excuse me? At least n. Right, because this thing, when there's an arrival at t, it already jumps to that new value, right? So yes, there is at least n arrivals. Can you see that? If this means the nth arrival already happened by time t. So this implies that n of t is bigger than or equal to n. Any problem here? What is your name, please?
Ankara.
Alperen. Yes, of course. I think I asked before. Or maybe not, yes. Okay. So, how about the other way around? Does the right-hand side imply the left-hand side? You're shaking, you're nodding. Why?
Because if we have more than n arrivals, that means we should see the nth arrivals before.
Right. Maybe this is a little tricky to understand, so let's break this. You're right, essentially. But to argue with perfect confidence, maybe we can split this into the union of two events, n of t bigger than n, union n of t equals n. Either bigger or equal. In the case that it's equal, n of t is equal to n, we know that the nth arrival has happened by time t. So at time t we have reached the level n. At least we have exactly reached the level n. So the nth arrival happened by time t. So Sn is less than or equal to t. Right? How about this one? N of t is bigger than n. Why? I mean, the nth arrival happened, but even more arrivals have happened by time t. So in this case, clearly the nth arrival is before t. So when we combine these two, we see that, yes, the right-hand side implies the left-hand side. So we have shown equality between Sn less than or equal to t and n of t bigger than or equal to n. Any questions? So let's call this number 1. For number 2, I claim that Sn is bigger than t is equivalent to, do you want to complete the rest? N of t bigger or smaller than n? How can I argue that this is true? Complement, exactly, very nice. Your name again? Taner. Taner put it very, very elegantly. Because if you complement this, So we know that we know already that this is equal to that, but the complements must also be equal. Okay, so what is the complement of that? Sn bigger than t, and the complement of this n of t is less than n. So we proved that this is true. All right, let's do another one. How about Sn bigger than or equal to t? So Sn bigger than or equal to t means the nth arrival is happening after or at. So Sn is somewhere either at t or after t. All right, so what does it tell me in terms of n of t? If it happens at t, n of t is n. If it happens after, it's less. Right? So can we say that this implies that n of t is less than or equal to n? Yes. We already argued. So if it is at t, if Sn is at t, then n of t would be equal to n. If Sn is after t, n of t would be less than n. Okay. Does the right-hand side imply the left-hand side? What do you think? Who said that? Name again? Atakan. Atakan, of course. Yeah. Atakan, Alperen, and then Eren, Semanur, Taner, Emin, Kaan, Mustafa, Alperen, and you? I will try to. Can you repeat that? Maybe you can spell it. Jem. Okay. That was not that hard. Sorry. How about you?
Enes.
Enes. Anybody I skipped? Mert and? Kaan. Mehmet. Very nice. Awesome. So, so basically, Atakan suggested that this is not true. Why not?
Because we already said that n equals nt of n equals n shows that s of n smaller or equal to t. So it can be more left to the side if it's equal.
I see. So if n of t happens to be, you know, I didn't get it.
Before t, like if Sn is before t, but Sn plus 1 is after t, n of t is equal to n, but Sn is not greater or equal to t.
Right. Another way of seeing this, we can break it into two, again, like we did over here. This is the union of n of t is less than n, and n of t is equal to n. In the n of t is equal to n case, yes, Sn, in this case, so maybe let's do this case first. In this case, n of t is less than n. Clearly, Sn is bigger than t, yes. But in the n of t equals n case, as Atakan pointed out, Sn may have happened before t, right? In this case.
Has to have happened
Before or at. Sn is less than or equal to t, right? Because at t we have level n reached. Therefore, Sn must be at or before. Okay, so this means this does not imply the left-hand side. Okay. Shall we do one more? Which one should we do? There is one in your lecture notes. Maybe you can, yes, Mustafa?
But if we take the union, does it imply?
The union means Sn is either bigger than t or less than or equal to t. So it doesn't really tell us anything. Right? Mm-hmm. Any other? Do you have a question, Taner? Emin? Eren? No? Okay, so shall we do one more? There's one more, I guess, in the lecture notes. What is it? Complement of this one? Sn less than t. Sn less than t. Clearly, since it's the complement, it would imply, right, n of t larger than n. But if you want to see it directly, well, by time t, the number of arrivals so far is less than n. This is below n. And it will reach n after. I mean, clearly, right? I mean, Sn, because Sn is strictly after t. So it will reach n at some time after t. So basically, then n of t must be, oh. Huh? Oh, what am I doing? Sorry. Erase all that. Sn is before t. So clearly, the level n has been reached. So basically, at time t, the number is before larger or equal to n. I said larger or equal. So then this is not true then.
It is, but it is incomplete.
Huh?
It is, but it is not complete without the equal.
Right. So maybe this is the case. Really? Right? This is the case. So then our argument of going from this to that was not true. It is not an equivalence between the two anyway. Okay, so this would imply that. In order to see it better, this says n of t is equal to n, or n of t is bigger than n. N of t is equal to n. This means Sn is less than or equal to Now there's a problem. What do you think?
Yes, the implication is in the other way.
Right. Doesn't matter, right? Because if Sn, so basically by doing this, we are already showing that the other way is not true. Okay? So this means that Sn is less than or equal to t, and this means that Sn, the time of the nth arrival, is before t. Okay. So this is sort of bigger than the left-hand side. It does not imply the left-hand side. But the left-hand side implies the right-hand side by this pictorial argument. Sn less than t means that the nth arrival has happened. Okay? So the number of arrivals at time t is at least n. Any questions? Any comments? So what is next? Why did we study this? Because we will study the Poisson process, which is a very powerful model for modeling arrival processes in many scenarios where a lot of random effects come into the picture. Just like we use the central limit theorem to model the value of a random quantity when a lot of independent effects add in, such that their overall effect looks like a Gaussian, a bell-shaped, with a bell-shaped PDF. Just like that, when we have a lot of independent, well, very rare occurrences or arrivals, their aggregate can often be modeled with a Poisson process. In order to understand the Poisson process, of course, we needed two ingredients. A Poisson process is a counting process where the inter-arrival times, the xi's, are IID exponential. So we had to understand how exponential random variables work, the memorylessness property, etc. Remember the bus arrivals that I was telling you about? We considered it for one bus. Now we'll be able to have a lot of interesting examples when we consider a succession of bus arrivals. Okay, so do you have any questions about counting processes? If not, then this is all for today, for our discussion on counting processes. Next time we will continue with Poisson processes.